There will be some presentation, some informal presentation about Apple. And then tonight is the dinner, the banquet. It starts at 7:15, I think, and all the instructions are in your files, how to go there. Everybody goes independently and returns independently with public transportation.
Okay, the final session of today, we'll have to deal again with three very interesting talks on these unexpected ultraviolet properties of maximally supersymmetric theories. The first talk is by Dr. Cachazo. What is the simplest quantum field theory?
All right. Okay, thank you very much. Of course, I have to start by thanking the organizers by letting me talk here in this very nice conference, and also for putting together a very impressive meeting, which I know very well how much effort it takes. And today I'm going to be telling you about what is the simplest quantum field theory, at least in my opinion. Can you hear me? Can you hear me okay at the back? Okay. Either you cannot hear me or you are so happy that you don't say anything. Okay, very good. So this is work based on a recent paper with Nima Arkhani-Hamed and Jared Kaplan. But I have to start by giving you a more precise formulation of the question. So I want to make the question in quantum field theories in 4 dimensions. And the simplicity that I'm talking about is at the level of the S matrix and in perturbation theory. So most likely I won't have time to finish the talk, so I'll give you the answer right away. And the answer is n equals 8 supergravity. The naive reason is, of course, a large amount of SUSY. That's what we would say. But the goal of this talk is the following, is to give evidence that there are many more surprises which are not a consequence of supersymmetry and are genetic to theories with high speeds. SUSY, all it does is to allow us to show that those properties extend to all other particles in the theory, even the wildest of all, which are the scalars in this picture. And the main property, which is something that I would like you to take away with you from this talk, is that there is an amazing convergent behavior for infinite complex momentum. And that's the key to all the properties we're going to see today. So what is the claim? The claim is that n equals 8 supergravity has the nicest S matrix in 4 dimensions. Well, I'll try to provide some evidence for that, and let me just mention a few of them. The entire 3-level S matrix is determined recursively in terms of the 3-particle one, which is completely fixed by Lorentz symmetry. Okay? The massless S matrix exists in the whole modular space, and there is an E77 symmetry that has a very simple action on the 3-level S matrix. And finally, what I'm going to show today is that the one-loop S matrix is determined by the most special and simplest kind of all singularities, which is called the Lydian singularity. And I will end by making a conjecture, and the conjecture is that the entire S matrix is determined by its Lydian singularities. And this is the nicest property a field theory can have, at least in perturbation theory. And this implies, among other things, that the theory is finite and free of UV divergences. Okay? So since this is the simplest field theory, probably I should start by a very simple calculation, like a 9-loop calculation, right? But I'm not going to do that. I'm just going to say something that probably is crossing the minds of many of you here, which is that, of course, being finite is not very exciting by itself. The reason is that the expansion parameter is the energy divided by m Planck, and this means that this is an asymptotic expansion, and that non-perturbative effects are large as super-Planckian energies. Moreover, the E77 symmetry must be broken down to a discrete subgroup by black holes. And all this is consistent with the impossibility of decoupling it from M theory. Of course, as we also know, the interesting features of quantum gravity are really a consequence of the breakdown of local field theory, and it has to do with the holographic description. So why am I doing this? Well, to us, or to me, the real interest is that all the structures I will explain today, and the ones which are yet to be found, hint towards the existence of a dual formulation of this theory. N equals 8 supergravity seems to be the prototype where to fully test and develop the ideas of the analytic S-matrix program from the 60s, okay? In the 60s, people were studying S-matrices, and they were finding, well, many people that I talked to, they say that everything was very difficult and that there were all these cuts, and you could actually get cut if you tried to go through the books and the papers. And to me, the reason is that the program was so difficult because it was being applied to a very difficult theory, perhaps the theory of scalars. Now, what could this dual theory be? Perhaps it's a twist or string theory for gravity, or more generally, a topological string theory. And this duality would imply finiteness while being non-perturbatively incomplete. Okay? And this was already hinted by Witten in his 2003 paper, and by many other people later on. Okay? So we're not going to start with 9 loops, we're going to start with a 3-level S-matrix. So Lance gave us this morning a very nice framework for my talk today. But in order to be self-consistent, let me start by describing the main tool for this talk, which is called the BCFW deformation. And the idea is basically the following. You just search for a one complex parameter family of deformations of the scattering amplitudes and compute it so that you can compute it by using its physical singularities. The idea is that you take the momentum of 2 of the particles and you try to find a deformation that preserves momentum conservation. That's why you add this deformation here with plus sign and this one with minus sign, such that these particles are still on shell. It's very easy to find that the only way to do that is with a complex vector Q, and the way to see it is by choosing P1 and P2 to be back-to-back, and choose units in which the energy is equal to 1, so P1 and P2 are given by this, and the only Q that can satisfy all the properties is something like this, or its complex conjugate. So Q and Q bar will play an important role in this talk. Now, at 3 level, the amplitude becomes a rational function of Z, so we have our rational function, and therefore it can be computed by just knowing its singularities. So all the singularities on the Z-plane at finite locations are just given by the propagators of the 3-level S-matrix, and we know what happens when you approach one of those propagators. The amplitude factorizes, but we know that when you deform the contour, you can also pick up a contribution at infinity, right? Now, the physics at infinity might be very complicated, and we don't know what it is in general. You might expect that for the scalar field theories, this amplitude, this function just goes to a constant at infinity, and for gauge theories and gravity, it will just blow up. Especially for gravity, we would expect that for large momenta, you will get something that diverges very badly. Well, not quite. Actually, scalars go like a constant. Young-Mills go like 1 over z, and gravity goes like 1 over z squared. I have to say that this is, one has to be careful here, because what I'm talking about is making this deformation where the helicity of the second particle is minus, and here you can have any particle with any spin less than 2. And here in Young-Mills, as long as you deform the particle 2 that has negative helicity, and anything that has a spin less than 1, you will have this behavior, okay? So this is already very surprising, and it shows that gravity, remember, this is pure gravity. Here I'm not talking about supergravity. Behaves in a better way at infinity than Young-Mills. Okay? From here, we deduce the fact that there are recursion relations. So the whole 3-level S-matrix can be computed in terms of smaller objects. And you can apply this recursion relation on and on and on, all the way until you decompose any 3-level S-matrix into the product of 3 particle amplitudes, which are completely determined by Lorentz invariance. So that's very nice. But what is the physics at infinite momentum? Well, Arkani, Hamed, and Kaplan gave a very nice interpretation of this. They said, well, if you're taking these 2 particles and you're giving them a very large momentum, because this z is going to infinity, this is like a particle that is blasting through a soft background. So we can use a background field method to understand what's going on, and they did. And they found that if you expand the the gauge field in Young-Mills, and little a is the fluctuation, you find that the effective Lagrangian looks like this, and it has an enhanced symmetry, which they call spin symmetry, where the Lorentz indices decouple from the Lorentz indices from the derivatives, and therefore you have more symmetries, and you can constrain the scattering amplitudes and show that they go like 1 over z. You can kill this term by using Ward identities. Now, pure gravity has 2 copies of the spin symmetry. This is why it's better behaved than Young-Mills. In fact, the number of copies of the Lorentz group that you get, the extra copies at infinite momentum, is equal to the spin of the particles that you have. Therefore, for 0 spin, it means that for scalars, you have 0 enhanced symmetries, and that's why the theories are not nicely behaved at infinity. Now, I hope that you are all thinking about this question at the moment. If pure gravity is so nice, why bother make it supersymmetric? Moreover, why bother make it maximally supersymmetric? Well, the answer to that question comes from unitarity cuts. We want to do loops, and as Lance said this morning, unitarity cuts are a very useful and powerful technique to understand loop amplitudes. And if you see, the regular unitarity cut that we learn in quantum field theory is the one that relates 2 3-level amplitudes, and you perform what is called a double cut, where these lines are propagators, and these lines are now on-shell particles. Now, if you perform a deformation of the internal particles to explore the UV behavior of this object, you find that on one side, if you make the deformation that makes the amplitude well behaved, on the other side, you are forced to have the deformation that makes the amplitude badly behave. Okay? So pure gravity will not show anything very, very nice at loop level. So the hope is that supersymmetry will allow us to extend the nice behavior of one side all the way to the other. Very good. Now, part of the whole complication is that we have all this plethora of objects with amplitudes with plus, minus helicities all over the place. And the reason we have to have all that complication is that CPT forces us to add for every particle with helicity h, a particle with helicity minus h. This discreteness is a source of complications. And this is how maximal supersymmetry comes to the rescue and fixes these problems and allows us to replace the whole mess by very smooth objects. Basically, the reason is that multiplets are CPT self-conjugate. So instead of talking about plus and minuses and amplitudes that depend on all this, we simply introduce some coherent states, which I'm calling eta and eta bar, which are built by starting with a particle with the smallest helicity, minus s. In Young-Mills it will be -1, in gravity will be -2. And then apply this operator with a Grassmann parameter here, and with a reference spinor, which is fixed, and the corresponding supercharge. Okay, so this object here encodes all the content of the supermultiplet in one single nice object. I can also do the same thing with the Q bar supercharges, and I get what I call eta bar. The two representations are perfectly good representations of the same thing, and they are related by a Fourier transform. Now we can think about scattering amplitudes as being completely smooth objects of these eras. Okay? So from now on, I will not be talking about plus, minuses, spin, -3/2 or 1/2, scalars, and so on. I'll just have amplitudes that depend on these eras. Okay? Now, supersymmetric Ward identities, we know very well, are very useful things, but sometimes are very hard to write down and very hard to use. Well, in this language, under Q SUSY, the amplitudes just go under they just go to a translation of the eras by some spinor, by some Grassmann variable μi, and this is what the supersymmetric Ward identity is telling you, that you can just simply take this amplitude, shift it by some quantity μi, and you get the same answer. So that's the full content of the supersymmetric Ward identity, and that's what we're going to use. Now, of course, you might have thought that I didn't tell you what n equals a supergravity is because you all know the Lagrangian by heart, right? And you can write it down immediately if I ask you to. Well, no, that's not the reason. The reason is that I had another idea in mind, is that now I'm ready to define for you what n equals a supergravity is, which is the object of study of this talk, without even writing a Lagrangian. And the idea is that I'm only interested in the n equals a supergravity S matrix, which is given by these objects, and where the one particle states are given by these coherent Grassmann states, where I start with a spin -2 or +2, and the index I goes from 1 to A. So I have A supercharges, I build my states out of these things. Now the index structure naturally gives rise to an SU8 R-symmetry group, and of course, once you reach the scalars, you find 70 scalars, and they transform in the 4-index antisymmetric representation. Now, many people have studied this theory, okay? And it would be very hard to make a complete account of everything that has been done. So I made an attempt here. And I'm sure I'm missing many people, so my apologies to everybody that is not in this list. But as we heard today, there are many different approaches to look at n equals a supergravity, and it's becoming a very interesting research direction. So let's see how Susie can help us with these recursion relations. Okay? I want to claim that I can write down recursion relations for any amplitude in n equals a supergravity. And you would say, well, that's completely silly. You just told me that if you have an amplitude where you only have scalars, this thing doesn't vanish at infinity, and you will not be able to write down recursion relations. Well, the key point is that if one approaches infinity in a supersymmetric way, then all amplitudes vanish at infinity. The idea is to make the same deformation we did before, but at the same time we deform the Grassmann parameter in this form, in this way. Once you do that, one can show that all amplitudes, no matter what they are, remember that here eta encodes all the supermultiplet. I'm not talking about gravitons, scalars, or gravitinos, anything in particular. The amplitudes go to 0 at infinity, and you can write down a recursion relation. So you might say, well, how do you prove that? Well, here is a very difficult proof of the statement. You just use the Q SUSY to shift eta 1 of Z and eta 2 of 0 to make the amplitude look like a minus minus Z amplitude, which I told you vanishes at infinity as 1 over Z squared. So it's just a consequence of SUSY. Somehow SUSY allows you to bring the good behavior of the high spin particles to the whole object. You might also wonder, well, how can this be? What happens to the divergence that you found for the scalars? Well, what is happening here is that the price you pay is that when you shift, you also shift all the external particles as well. So this is a recursion relation between the whole supermultiplet. It's not a recursion relation of gravitons in terms of just gravitons. It also relates, say, an amplitude that has gravitinos to smaller amplitudes that can contain scalars, gravitinos, and gravitons. But the important point is that all amplitudes now can be computed using recursion relations down to 3 particle amplitudes, which are completely determined by Lorentz invariance. You might have said, well, you didn't tell me what the Lagrangian was. How do you know the interactions? My claim is that I don't have to give you the interactions. I don't have to tell you what the interactions are, because everything is determined by Lorentz invariance. And this is why I didn't have to give you a Lagrangian. Okay. But you would say, well, Lagrangians are very useful, right? We can learn many things from them. One of the things we have learned from Lagrangians, especially for n equals a supergravity, is that there is a vacuum structure, there is a modular space, and there is a nonlinearly realized E77 symmetry. Well, this is one reason why n equals 4 superjambians is not as nice as n equals a supergravity. The nicest massless S matrix is only there for n equals 4 superjambians at the origin of the modular space, while for n equals a supergravity, the whole S matrix goes through nicely through the whole modular space, okay? And the modular space is parameterized by 70 scalars, okay? In the form, as I mentioned before, in the antisymmetric 4-index representation of SU8. Now, there is something interesting that happens here. You can take the commutator of two of those objects and write it in terms and give rise to something that is a rotation in SUA, okay? And you can try to check if these commutations can give rise to a nice Lie algebra. And it turns out that in general, if you were trying this for SU7, it wouldn't work. For SUA, it does work, and it gives rise to an exceptional algebra. It's a real form of E7, which is called E77. You have the 63 generators of SU8 plus the 70 scalars make up the 133 generators of E77. And this is roughly the commutation relations that you have. These are the generators of SU8. Now, what I want to discuss is how do you see all this from the S matrix, okay? Somehow I can tell you that already seeing this from the Lagrangian is a difficult task, and the full nonlinear action of the E77 was actually obtained by Renata and collaborators earlier this year. But I want to see how this manifests itself in the S matrix. So the way to explore the possibility of a modular space, if you didn't know that there was one, is to look for single soft emissions, okay? And now one can see that using the recursion relations, one can show that if you have a single soft graviton, there is a divergence, but that's not surprising. Weinberg told us in the 60s that that's true. Graviphotons give a finite answer, showing that there is something interesting there, maybe something related to the work of Maldacena and Berkovits, but we don't know yet. And when you do it for the scalars, you find that they all vanish. If you take a singular scalar to be soft, every single amplitude that contains a scalar that goes soft vanishes. And that's the indication of a modular space. Now, but how do you see the E77 symmetry? Well, you take the double soft emission, right? And then you would say, well, naively, if I give a Beth to one of the scalars, then I can map the Hilbert spaces, right? And then the symmetry will tell me that if I expand the one particle space in this form, I should find that when I plug these values in the scattering amplitudes, I get 0. And that will be the statement of the invariance and the statement of the symmetry. But there is a puzzle. I should see the commutation relation that gives rise to E7. And this is antisymmetric, of course, while both statistics tells me that these amplitudes, when evaluated at the double soft, when I take the double soft limit, they should be equal by both statistics. So there is a puzzle here, okay? Well, the answer or the resolution to this puzzle is very simple. You started with the wrong object here. Q doesn't really exist without a regulator. And while the double soft limit is finite, it is ambiguous. In other words, it depends on the way it is approached, okay? And this is good. Precisely the non-abelian structure we are very familiar with usually comes from the presence of curvature, from the fact that the endpoint depends on how you approach the point, okay? So we did the calculation. We took two scalars with these indices. These are fundamental indices, and these ones are anti-fundamental indices. We took an amplitude that has these two scalars, and we took the soft limit and tried to see what happened. What we found was that using the recursion relations, you can prove that all this thing does for you is that the two scalars disappear completely from the story, and you get the action of a rotation with an angle given by this, where the two p's are going to 0, but you see the answer is finite, but it's ambiguous. It depends on how you approach the limit, and an operator which is in SUA. So you clearly see how the action of E77 is manifested at the level of the S matrix. Basically, the two scalars take a hard particle and rotates the amplitude. This doesn't happen for n equals 4 superjumbles, as we know. You take the double soft limit and you get a divergence, okay? Now we're ready to go and explore one loop, the one loop S matrix of this theory. Once again, there is being a lot of work done at one loop, and here are some references. What I'm going to talk about now has strong overlap with the work of Forde. So once again, Lance this morning gave a very nice background for this talk, so So I can probably go very fast here because all you are experts now in computing loop amplitudes and using the unitarity cut method and everything, right? And generalized unitarity and so on. But let me start by telling you, reminding you that at loop level, not only we have poles, but we also have branch cuts. And the discontinuity is computed by using the unitarity and computing a double cut. We get, say, at one loop, we have functions like log squared, and the discontinuity of a log squared is a log, right? Well, what the meaning of all this is going to come clear in a few minutes. Now, this log squared has a discontinuity, right? Which is proportional to a log. But a log also has a discontinuity. So what's the meaning of the discontinuity of the discontinuity? Well, that's what happens when you cut one more propagator, and this block represents 3 level amplitudes here, and the triple cut computes for you the discontinuity of a discontinuity. Now you can continue the game, right? And in d dimensions, if you compute a d cut, okay, you cut d propagators, that computes the discontinuity across what I call the Lydian singularity. Okay? And the Lydian singularity is the highest codimension one. It's basically the intersection of all these branch cuts in this very complicated, higher dimensional complex space of kinematical invariance. Okay, so when d is equal to 4, the Lydian singularities are computed using quadruple cuts. Okay, 4 cuts, d equals 4. That makes sense. The claim, one loop amplitudes in n equals a supergravity are determined by their Lydian singularities. Okay, so that's what I want to prove now. You would say that naively this is impossible. How can a function with many branch cut singularities be determined only by knowing the discontinuity across the highest codimension branch cut? If this is true, it must be just a property of very, very special functions, right? It's like knowing very little information about the analytic structure of the object, and you can determine the whole object. That's almost, that's very hard to believe. So let me try to give you the construction. The idea is that you start with the highest codimension singularity, the quadruple cut, and you try to model this by saying, well, you can model the behavior of the Feynman diagrams by having a very simple object, which is a scalar box integral, which Lance defined today for you. Okay? So we start with this. We are very happy. This is a Lydian singularity. Now you look at triple cuts. I don't have time to show this to you, but it turns out that the triple cut integral over the Lorentz invariant phase space becomes a complex integral, okay, a contour integral in the complex plane across a branch cut singularity here. And you can deform this contour integral and pick up contributions in the complex plane from poles that are poles where these amplitudes factor, and therefore these contributions here are nothing but quadruple cuts, and there is a contribution at infinity. In other words, the singularities associated to a triple cut are given by the quadruple cuts we already computed, plus a mysterious contribution at infinity. Okay? Now, if this mysterious contribution at infinity was 0, then all triple cuts are determined in terms of quadruple cuts. Okay? That would be fantastic, right? That's precisely what I'm trying to tell you, that the structure will be completely determined by quadruple cuts. So you can compute this thing at infinity here by doing this integral, and you can show once again that by using SUSY, you can relate all these amplitudes and the behavior of these amplitudes to the nicest behaved ones, and show that this vanishes in n equals a supergravity. And this means that no scalar triangles are needed to reproduce the singularities of Feynman diagrams. Well, you succeeded there, and you continue. You say, well, let's take double cuts. Once again, a double cut can be written as the sum of triple cuts plus a mysterious contribution at infinity, which again vanishes in n equals a supergravity. So what we have found is that double cuts are determined in terms of triple cuts because of this nice behavior at complex infinity. Triple cuts are determined in terms of quadruple cuts. Therefore, all the singularity structure is just completely determined in terms of quadruple cuts, just due to this very nice behavior at infinity. Okay? An additional step is needed where you have to use dim rec, okay, where you have a single cut. And I don't have very much time to discuss here, and this is work in progress. But one can argue that also rational terms are not there. Okay? So let me give you a summary of what we have found up to now. Is that one loop amplitudes in any quasi supergravity are completely determined by their leading singularities. In other words, all one loop amplitudes can be written as a sum over scalar box integrals in d equals to 4 minus 2 epsilon dimensions with coefficients which are rational functions of the external kinematical invariance. This is a statement of the no-triangle hypothesis, restated in terms of this leading singularity. And this was proven recently by Berger, Bohr, and Van Hook using a stream-based method for reduction procedures. Okay. So, what is the one-loop solution of any quasi supergravity? Any one-loop amplitude can be written in this form, where the coefficients are completely determined by the product of three-level amplitudes, which can all be computed by using recursion relations all the way down to 3 particle amplitudes. So the whole structure to one loop is completely determined by Lorentz invariance. So let me finish with a discussion of the leading singularity conjecture. So the conjecture is that the S matrix of any quasi supergravity is completely determined by its leading singularities. At L loop level, the leading singularity is computed by a 4L cut, which completely localizes the loop integration variables. Of course, you might say, this is silly, right? For 4 particles, you only have 7 propagators, and this is 2 loops, and I'm claiming that you can cut 8 propagators. So this is completely silly, right? Well, not quite. You can show that once you cut these 4 particles here, this diagram reduces to something that looks like this, and where this particle, this scattering amplitude now has hidden singularities that you didn't see from this point of view, and you can actually cut 8 propagators and continue the game all the way down to just a 3-level amplitude. Very good. So, what would it take to explore further the leading singularity conjecture, or to actually prove it? Well, first of all, one would have to generalize it to include dimensional regularization in order to understand very well these rational terms and what they are doing. At higher loops, these rational terms manifest as what people call new terms. So they would also have to be included in the procedure. It would require a careful study of the Lorentz invariant phase space integrals for higher loop amplitudes in order to see how this structure of everything being determined in terms of the leading singularity emerges, as we saw it at one loop. Now, maximal SUSY, as I remind you, is there only to relate the infinite complex momentum limit to that of the very well-behaved gravitons. And the good behavior at infinite complex momentum of graviton amplitudes comes from something that is not related to SUSY. So that's an important point that I want to get across in this talk. Now, what are consequences of this leading singularity conjecture if it's true? Well, all the S matrix is determined algebraically in terms of the 3-level amplitudes, which are determined by Lorentz symmetry. If at any group level the S matrix fails to be determined by the leading singularity, it will be a sign of a UV divergence. So we are very familiar with that. For instance, at 3-loop in pure gravity, one will have to include all plus and all minus 3 particle vertices, which are not there at 3 levels, and these are generated by the 2-loop contour term. So let me finish the talk by giving some future directions. Well, the first one, of course, is to prove or disprove. So any of the two will be fine. The leading singularity conjecture. Okay? The second one would be to find a dual theory. It would be also very interesting to construct the finite action of E77 on the S matrix. Remember that I only gave you the first order action of E77 on the S matrix. Understand the connection between the presence of E77 and the other properties of the S matrix. This is something we still haven't done. It would be interesting to do. And finally, start the exploration of higher dimensional field theories. Thank you.
Is there any question?
There is one. You want it?
You said that you didn't know any properties of the Lagrangian other than Lorentz invariance. And
Can you use the mic?
You said that we didn't need to know any details of the Lagrangian other than Lorentz invariance and supersymmetry in order to derive all these properties. Right, but all of those properties would also be true of n equals 8 supergravity plus any n equals 8 supersymmetric counter term that you could add, you know, by integrating over all of superspace. So there's obviously some property that you're using, and whatever it is, it's relevant to finiteness, because if you throw in arbitrary, you know, higher dimension terms that are Lorentz invariant and supersymmetric.
No, I just told you. Like in the example of the n of pure gravity, you will discover that there are new vertices that are generated by the UV divergences. Here, all I'm saying is that if you start with n equals 8 supersymmetry, right, the three particle amplitudes are completely determined, and they just give you everything else. If you start generating, or you start using, if you start generating something else that wasn't there from the start.
But you can throw in any supersymmetric term that you like at the start at tree level.
Yes.
Okay, but the fact that those terms are absent, how was that encoded in?
Those will spoil the behavior at infinity.
Okay, that's the
terms will spoil the behavior at infinity.
Okay.
Oh, that's a very good question. Thank you for asking.
Next. Yeah, I had a question about the argument that the rational terms vanish in one loop. So you often get these spurious singularities that cancel between terms and rational terms. So how do you know that there aren't spurious singularities with box gram determinants in the bottom, in the spurious gram determinants in the bottom of the rational terms that cancel against the box terms in the one loop n equals 8 supergravity?
Well, for n equals 8 supergravity, we are strongly using that, say, for the collinear limit, that the collinear limit is not renormalized, that's very nice, and that factorization, the factorization is also very well behaved. So what you're saying is that for rational, there are spurious singularities, you're saying?
Yeah, so I might be able to write a candidate rational function that has no collinear or soft or factorization properties, but because I've put denominators, which are gram determinants, which cancel against similar terms in the box coefficients. Because you know there are box coefficients, and so you have to argue a little bit about what they look like, maybe.
Yes, that's right. So the whole point is that just by using the physical singularities, right, you can actually, and of course allowing for complex deformation so that you don't hit phase-space singularities, I mean just phase singularities. You can actually show that the set of rational functions that you can possibly have, is very small. Okay? And then you can simply show that their coefficients have to vanish.
Does it answer your question?
Yeah, we could discuss it afterwards. Because I think in principle you can build up large powers in the denominator with these spurious poles that keep you from having to put.
I mean, these spurious poles, if you multiply them, if you make one of them, you take the complex conjugate and you put them together, they give you the Jacobians of the box functions or things like that. And those are known to cancel, to always be zeros of the coefficients of the amplitudes. And that's something that you can show by looking at the three particle, at the quadruple cut for real momentum. You can show that the coefficients must have those zeros, which are the grand determinants that you're talking about. But we can talk, I mean, that's a technical.
Since we are late, I allow one more question. Is there anybody want to?
There is more.
So I have a comment which actually relates to the end of Michael Pinto about symmetry. And so SL2R is a subgroup of E77. And one of the important things which we have to find out is whether it is broken SL2R to SL2C or not. Because then it will mean that also E77R is broken to E77C. So if the symmetry is continuous, we have another current which has to be conserved. And it controls various things, in particular the one which you explained. However, if the symmetry is broken to discrete, there is no network charge.
Yeah.
And so then things are complicated. So it is an issue of SU8, parallel SU8 anomaly, which we don't know. And this is something which I'd like very much
Very good.
stress, that
Yes.
this is what is missing in the story. Thank you.
Yes, of course. And as I mentioned, the fourth point is to understand the relation of this C77, if it's there, to the properties of it. Yes, that's right. That's right. That would be the zeroth order question, right? If it's not there, then the answer is that there is no relation.
So you're saying that his analysis is correct under the assumption that there is no SU8 anomaly.
No, our calculation is at 3 level.
At 3 level is okay.
So
Yes.
if at the loop level, E77
Yeah.
continues in D equals 4, which we don't know, then we have some chance.
Yes, indeed. I mean, if you remember the calculation of E77 was done at 3 level, and then after I finished that, we started the one loop discussion.
I think we have to stop now.
Yes.
Thank you very much again, the speaker.